Review electromagnetic waves. So here's the notion, right? An electromagnetic wave is actually a transverse wave, okay? There is an electric field, and that's in the vertical direction here, the y direction, right? And there's a magnetic field that's actually perpendicular to it, right? That's in the xz plane, where z is the dimension coming out toward us, right? And the way that, here's how you'd make light, right? You just get or make a electromagnetic wave, right? Is get a transmitter, and then you just make a little antenna like this, and then you make this side positive and this side negative. So you pump the electrons over to this side, pump them out of this side, right? And then you pump them back the other way, right? And make this side negative and this side positive, right? And what that does is it makes the electric field change from being, well, at first it was this way, right? And now, or now it's this way, right? And at first it was this way, right? So you're changing the electric field from side to side. And then here's the rule. If you change an electric field, a changing electric field makes a magnetic field, right? And then we, of course, know that a changing magnetic field, this is Faraday's law, right, makes an electric field, makes a current flow, right? And so here's the deal, right, is that if we sit there and shuffle this charge back and forth from this side to this side, we make this electric field that's changing, and this is what we see here, right? And this changing electric field creates a magnetic field. The magnetic field creates an electric field. The changing electric field creates the magnetic field. And this goes on forever. And the reason why it just can't, like the electric field can't collapse and go away, is that electric fields contain energy. And so do magnetic fields. So if they collapse, the energy has to go somewhere, and the place that it goes is into the other kind of field, right? So a collapsing electric field makes a magnetic field. A collapsing magnetic field makes an electric field, right? And this thing bootstraps itself and goes through space like that, right? And then the question is, what does it travel through? Well, it turns out that electromagnetic waves can travel through nothing, which makes it very interesting to think about, well, what if we approach this wave from the front? What speed do we see it traveling? But that's, chapter 26, okay? And then the second thing is that up until what we're about to learn here, right? Okay, electromagnetic waves were believed to be waves. They did wave-like things. Okay, waves they refract when they hit water. They bend. We can get them to interfere with each other. Electromagnetic waves, just like we learned last year in the wave unit, right? So for sure there was no dispute about whether they were waves, until what we're about to learn in atomic physics here. Okay, so that's concept zero, is that we're talking about electromagnetic waves. They have no medium. They can travel through space, right? And then here's some other things, right? These are the wavelengths here. This is the spectrum, the visible spectrum. Notice that it's about from 400 nanometers to about 700 nanometers is what we can say. This is the large wavelength then, so red is large wavelength, blue is the short wavelength. This is high frequency, this is low frequency. High frequency, low frequency. Okay, and then notice that spectrum, this up here it's flipped, right? But here it is in its proper order. This is large wavelengths to short wavelengths, right? And that the visible spectrum is just this little bit that we can see with our eyes, right? Okay, and then notice that it's, we can do the cheer, right? It's radio waves, microwaves, infrared, light, ultraviolet, X-rays, fight, 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 gamma rays, yeah, physics. Okay, we'll maybe do that cheer in class because we need to remember that, right? Okay. The other thing that you need to know is that these waves gain energy, right? Radio waves, probably pretty safe. Microwaves, by the time you get into here, about 2 meters or so. Okay. You're talking about cell phones. You're holding that thing to your ear. We're not sure that's safe. I'm pretty sure you wouldn't want to put a microwave beam right up to your head. Infrared, obviously, that's like the what you feel from like a bonfire. Ultraviolet gives you sunburn. X-rays, people leave the room when they give you X-rays, and then gamma rays are actually used to sterilize meat. Okay, so yeah, we're getting more and more energy, more and more danger from these things, right? And then here are some things that we're going to do for as far as calculations. Okay, This is the basic wave equation that we used for 80% of our wave unit, is that velocity is frequency times wavelength. Okay, but for all electromagnetic waves, v is the speed of light, and the speed of light is c. That's a constant, a physical constant, and conveniently, it's with 3 sig figs, it's 3.00 times 10 to the 8th meters per second. It's actually 2.99 something or other, but there it is, right? This is frequency, it's in hertz, right? And then wavelength is in meters. Now, visible light is so small that we talk about nanometers. So a nanometer, nano is just 10 to the minus ninth. And then keep in mind that visible light ranges from the red end, low frequency end, to 700 to 400 nanometers roughly. Now, you know, a nanometer is approaching the size of atoms. Atoms are about 10 to the minus 10th meters, and the nucleus of the atom is 100,000 times smaller than that. So this chapter, we're actually going to deal with pretty small things, okay? So I'm about to change the slide here, okay? But let's do an example of this, right? What is the wavelength of a 91.1 megahertz radio wave? A couple hints. Well, the first hint is that the velocity is the speed of light, right? Okay. The second hint is that 91.1 megahertz. Mega is just 10 to the 6th. Okay, that's another multiplier, right? So that equals 91.1 times 10 to the 6th hertz, right? Now we're all set. We're going to use V as F lambda, right? And now we can just plug in numbers, right? Well, if V is F lambda, then let's see. Lambda is just V over F, right? That makes sense, right? It's how far it goes in 1 second divided by how many equal parts the second is divided into, right? That means 91.1 million cycles, right? So I'm just typing this into the calculator, right? 3.00 times 10 to the 8th meters of total distance, right? Divided by 91.1 times 10 to the 6th cycles per second, right? Okay. So 3E8 divided by 91.1 E6, and that's 3.293 meters, right? Okay. Now, just a little word here. I talked about how you might make radio waves. There's also the antennas, like FM antennas. This is in the FM, the frequencies used for FM. Okay. FM antennas, when you buy them, when you get like a stereo receiver, they give you a little dipole antenna. This is called a dipole antenna, right? And if you make this antenna 3.29 or some multiple of 3.29 meters, it will actually be tuned to this frequency. So if the station is, say, over here, and those waves are coming at this thing's going to pick up that frequency the best. I actually used this in my house. I couldn't get KMHD, which is, I think it's 89.1 megahertz. So I did this calculation, figured out the length of the antenna, figured out where the station was, and put this thing so that the station was, the waves were hitting it perpendicular to this dipole antenna. And sure enough, I got KMHD, which is an actual jazz station, right? Okay, so there it is. I'm going to do some more examples, but they're all about the same thing. V is F lambda. You might, probably a good idea to at least do one of those.